Look up at the night sky for a moment. Somewhere out there, countless planets are quietly circling distant stars. They've been following those paths for billions of years, moving through space with astonishing precision. But here's the strange part. Stars possess immense gravity, strong enough to pull entire planets toward them. So why don't those planets simply fall straight into their stars? And just as puzzling, why don't they drift away into the darkness of interstellar space? Instead, they remain trapped in a delicate balance, worlds endlessly falling, yet never crashing, moving forward, yet never escaping. It's one of the most beautiful mysteries in the universe. From tiny atoms to enormous galaxies, nature seems to favor this same pattern of motion. A hidden balance between gravity and movement that shapes the entire cosmos. So in this video, we're going to explore a remarkable journey across scales, from the smallest particles of matter, to planets and moons, to galaxies themselves. And by the end, you may realize something astonishing. You are not standing still. Right now, you are traveling through space at incredible speed, on a planet that is constantly falling around a star. Across the universe, countless planets travel around their stars in graceful, repeating paths. Some complete a journey in a few months, others take centuries to circle their suns. Yet for billions of years, many of these worlds keep moving along nearly perfect routes. It almost looks like an invisible track guiding them through space. At first glance, this seems strange. Stars are massive objects with powerful gravity pulling everything toward them. If gravity is always pulling inward, you might expect planets to simply fall straight into their stars. After all, that's exactly what happens when you drop a stone toward the ground. But that isn't what we see in the sky. Instead of falling inward, planets glide sideways through space while slowly curving around their star. They move in paths so stable that astronomers can predict their position centuries in advance. It's like watching a cosmic dance that never misses a beat. And the mystery deepens when we think about the alternative. If planets aren't falling into their stars, why don't they simply drift away into deep space? Why don't they escape the star's gravity and wander off into the dark? Something seems to hold them in a perfect middle ground. So what exactly creates this delicate balance? What invisible rule keeps worlds moving in endless loops instead of crashing or escaping? To understand this cosmic stability, we first need to notice something surprising. Orbital motion isn't rare in the universe. It's everywhere. Once astronomers began observing the sky more carefully, a remarkable pattern emerged. Objects in the universe rarely sit still. Instead, they tend to circle around something larger and more massive. Movement in curved paths appears almost everywhere we look. Closer to home, the moon quietly travels around Earth. Every month, it completes a slow journey that shapes tides and lights the night sky. For thousands of years, people watched this motion without fully understanding it. Yet the moon's steady orbit is one of the clearest examples of this cosmic pattern. Zoom out a little farther, and the same behavior appears again. Earth and the other planets travel around the sun in long, elliptical paths. Some, like Mercury, race around quickly, while others, like Neptune, take over a century. But all of them follow the same basic rule. They orbit, and the pattern doesn't stop at planets. In our solar system alone, hundreds of moons circle their parent planets. Jupiter's giant family of moons moves like a miniature solar system of its own, each one locked into motion, each one tracing a path through space. So the universe seems filled with these repeating loops of motion. Moons orbit planets, planets orbit stars, and stars themselves orbit something even larger. But to truly understand why these motions happen, we have to zoom in much deeper. Because strangely enough, the story of orbits begins at the smallest scales of nature. To understand why objects stay bound in orbit, it helps to shrink the scale of our journey. Far smaller than planets and stars lies the world of atoms. Every piece of matter, from rocks to oceans to human bodies, is built from these tiny structures. And surprisingly, they reveal a similar pattern of balance and motion. At the center of every atom sits a dense nucleus made of protons and neutrons. Around this nucleus, electrons exist in regions where they are most likely to be found. They don't move like tiny planets in perfect circles, but they do remain bound to the nucleus. Something invisible holds them there. This happens because of a fundamental force of nature, electromagnetism. The positively charged nucleus attracts the negatively charged electrons, but electrons also possess energy and motion, preventing them from collapsing into the center. The result is a stable structure where attraction and motion balance each other. It's a bit like a spinning top on a table. As long as it spins fast enough, it remains upright instead of falling over. Motion provides stability, even while gravity tries to pull it downward. Nature often uses this balance between movement and attraction. So even at the smallest scales, matter organizes itself through delicate equilibrium. Particles remain bound because forces pull them inward, while motion keeps them from collapsing. This same idea echoes upward through larger and larger systems. And when we scale up to planets and moons, the pattern becomes beautifully visible. Now the pattern becomes much easier to see. On the scale of planets and moons, the invisible balance behind orbits reveals itself clearly. Gravity pulls objects toward one another, just as Earth's gravity pulls everything toward the ground. But planets aren't simply dropping toward their stars. Instead, they're constantly moving sideways through space. This sideways motion is called velocity. If a planet had no sideways motion at all, gravity would pull it straight into its star. But because it's already moving forward, something interesting happens. Imagine throwing a ball across a field. As it travels forward, gravity pulls it downward at the same time. The ball follows a curved path before it eventually hits the ground. Now, imagine throwing it so fast that the ground curves away beneath it. This was famously described by Isaac Newton using a thought experiment. If a cannon fired a ball fast enough from the top of a very tall mountain, the ball would fall toward Earth. But as it falls, the curved surface of the planet would drop away beneath it. Instead of landing, the ball would keep falling around the planet forever. And that's essentially what an orbit is. A planet is constantly falling toward its star under the pull of gravity, but its sideways motion keeps missing the star over and over again. The result is a continuous curved path, a cosmic fall that never quite finishes. Understanding orbits didn't just change astronomy, it transformed human technology. Once scientists understood the balance between gravity and motion, they realized something powerful. The same rules guiding planets around stars could also guide machines around Earth, and that idea opened the door to the age of satellites. Today, thousands of artificial satellites travel around our planet. Some relay television signals and internet connections across continents. Others watch the weather, track hurricanes, and monitor the changing climate. Each one survives in space by following the exact same orbital balance as the Moon. To place a satellite into orbit, rockets must give it the right sideways speed. Too slow, and gravity pulls it back to Earth. Too fast, and it escapes into deep space. But at just the right speed, the satellite falls around Earth instead of into it. This delicate calculation is known as orbital mechanics. Engineers carefully map the curved paths spacecraft will follow. They predict how gravity from Earth, the Moon, and even the Sun will shape the journey. Space travel is essentially navigation through invisible gravitational rivers. Every mission to the Moon, Mars, or beyond depends on this knowledge. Space agencies plan complex trajectories that weave through the solar system. Yet behind these complicated routes lies a simple truth. The same cosmic balance guiding planets also guides our machines through space. At the heart of every orbit lies a simple but powerful balance between two ideas: gravity and inertia. Gravity is the force that pulls objects toward one another. Inertia, on the other hand, is the tendency of an object to keep moving in the direction it's already going. When these two effects interact, something remarkable happens. Imagine spinning a ball tied to a string. Your hand pulls the string inward while the ball keeps trying to move outward. Because of this balance, the ball moves in a circular path around your hand. Orbits work in a surprisingly similar way. Gravity acts like the invisible string pulling a planet toward its star. At the same time, inertia keeps the planet moving forward through space. Instead of flying away or crashing inward, the planet follows a curved path. This continuous curve is what we recognize as an orbit. Isaac Newton first described this relationship in the 17th century. His laws of motion explained how gravity governs the movement of planets and moons. For the first time, scientists realized the same physics controlling falling apples also controlled the heavens. The universe suddenly became understandable through simple rules. Centuries later, Albert Einstein expanded this picture even further. According to his theory of gravity, massive objects actually bend the fabric of space-time itself. Planets then move along the natural curves created by this cosmic bending. So an orbit isn't just motion, it's a journey through the geometry of the universe. To understand why planets orbit the sun today, we have to travel back billions of years. Long before Earth existed, our solar system was nothing more than a vast cloud of gas and dust. This enormous cloud drifted quietly through space, cold and diffuse. But eventually, gravity began pulling parts of the cloud inward. As the cloud collapsed, something interesting happened. Tiny motions within the cloud, barely noticeable at first, started to grow stronger. The entire structure slowly began to spin, and once that rotation began, it couldn't simply stop. This is because of a rule in physics called the conservation of angular momentum. A simple way to picture it is with an ice skater. When a skater pulls their arms inward, their spin suddenly becomes faster. The collapsing cloud behaved in much the same way. As gravity squeezed the cloud tighter, its rotation sped up dramatically. The spinning material flattened into a wide disk surrounding a bright, newborn star at the center. Inside this disk, dust grains collided and clumped together. Over millions of years, these clumps grew into planets. Those early motions within the spinning disk never disappeared. The forming planets inherited that motion as they grew larger. Instead of falling straight into the sun, they continued moving along the paths set by the rotating disk. And those ancient motions still guide the orbits of planets today. Among all the planets that formed in this spinning disk, one happened to settle at a very special distance from the sun. Not too close, where heat would boil away oceans. Not too far, where water would freeze into endless ice. Earth's orbit placed it in a narrow region scientists call the habitable zone. Because our planet follows a stable path around the sun, the amount of sunlight we receive remains relatively consistent. Each year, Earth completes one full orbit in about 365 days. That steady cycle shapes the rhythm of life on our planet. It defines the length of our years and influences the changing seasons. The tilt of Earth's axis combined with its orbit produces the seasons themselves. As the planet travels around the sun, different parts of the globe receive more or less sunlight. This gentle variation drives weather patterns, plant growth, and the migration of animals. Life on Earth has evolved alongside this predictable cosmic motion. Our orbit also keeps temperatures within a range where liquid water can exist. Water flows through rivers, fills oceans, and cycles through clouds and rain. Without a stable orbit, Earth's climate could swing wildly between extremes. Life might never have had the chance to develop. So the quiet path our planet traces around the sun is far more important than it might seem. This invisible balance between gravity and motion shapes the conditions for life itself. But Earth's orbit is only one example of a much larger pattern, because the same kind of motion appears on an even grander scale across entire galaxies. If we zoom far beyond the solar system, the same graceful motion appears again. Our sun isn't sitting still in the universe. It's traveling through the Milky Way galaxy along a vast curved path. In other words, our entire solar system is in orbit. The Milky Way is a gigantic spiral galaxy containing hundreds of billions of stars. At its center lies an incredibly dense region dominated by a supermassive black hole. Stars throughout the galaxy slowly circle this central mass, each one following an enormous galactic orbit. Our sun is part of this slow cosmic journey. It moves through the galaxy at a speed of about 220 kilometers per second. Even at that incredible speed, completing one full galactic orbit takes around 230 million years. Dinosaurs appeared and disappeared during just one small fraction of this journey. From a distance, galaxies themselves look like giant spinning pinwheels of light. Their spiral arms sweep gracefully through space, filled with stars, gas, and dust. Gravity holds this enormous structure together, while motion keeps everything from collapsing inward. Once again, attraction and movement find a delicate balance. So the same principle guiding the moon around Earth and Earth around the sun also shapes entire galaxies. The universe seems to favor this elegant dance of motion and gravity. But that raises an even deeper question. Where did this universal tendency to spin and orbit come from in the first place? To understand where this universal motion began, we have to travel all the way back to the beginning of the universe itself. Nearly 14 billion years ago, the universe emerged from an incredibly hot and dense state known as the Big Bang. At that moment, space itself began expanding, carrying matter outward in every direction. But even in this early chaos, the seeds of structure were already forming. As the universe expanded and cooled, tiny variations in density appeared throughout space. Some regions contained slightly more matter than others. Gravity slowly amplified these differences, pulling matter together into growing clumps. Over millions of years, These clumps became the first stars and galaxies. Whenever large clouds of matter collapsed under gravity, another effect appeared. Any tiny initial motion within the collapsing material became stronger as the cloud shrank. Just like a spinning ice skater pulling their arms inward, the rotation accelerated. This process created spinning disks, swirling gas, and eventually orbiting systems. Because of this rule, called conservation of angular momentum, rotation is extremely difficult to remove. Once a system begins spinning, that motion tends to persist. Stars form inside rotating clouds, planets form inside rotating disks, and galaxies spin as enormous structures. The universe seems to preserve motion whenever gravity gathers matter together. So the orbits we see today are not accidents. They are the natural outcome of how matter assembled across cosmic history. From the earliest galaxies to modern solar systems, the same rule keeps repeating. And that leads us to a profound realization about our own place in this moving universe. Across the universe, motion seems woven into the fabric of existence. Moons circle planets, planets circle stars, and stars drift along vast galactic paths. Nothing appears completely still on the cosmic stage. Instead, everything participates in a quiet gravitational dance. These orbits are not chaotic or random. They follow elegant rules that balance attraction and movement. Gravity pulls objects inward, while motion carries them forward through space. Together, they create the graceful loops that shape the structure of the cosmos. On a small blue world orbiting an ordinary star, this balance makes life possible. Earth quietly circles the sun while spinning on its axis. That steady motion brings day and night, seasons, climates, and oceans. Our entire existence unfolds within the rhythm of an orbit. Yet for most of human history, these motions were invisible mysteries. People saw the stars moving across the sky but could not explain why. Only in the last few centuries have we begun to understand the physics behind them. Human curiosity slowly revealed the hidden mechanics of the universe, and that realization carries a deeper meaning. Every person watching the night sky is also part of this cosmic motion. We are passengers on a moving planet, orbiting a moving star, inside a moving galaxy. The universe is not static. It is a vast system of motion, and we are traveling within it.